Hi, my name is Tyler Brand, and my project proposal is titled Infinite Patience Algorithm, a Route Optimization Solution for Cold Chain Logistics. Billions and billions of dollars are wasted on an annual basis due to food spoilage and food waste. Approximately 33 to 40% of all food within the food supply chain will simply go uneaten or is wasted during transport, and this equates to approximately 149 billion meals worth of food that are wasted on an annual basis. Inefficient last mile logistics often leads to increased fuel consumption as well as increased carbon emissions. So there's a sustainability issue with this. And traditional optimization algorithms or models do not account for real-time constraints as well as perishability or food-related constraints. The overarching research question that I have for this project is how can modern constraints be integrated in the traditional optimization algorithms to enhance the efficiency, sustainability, and resilience of last-mile logistics, food supply chain, and regional distribution networks. The goal of this research is to create a new algorithmic framework incorporating real-time constraints as well as food-related constraints such as perishability, temperature control, and temperature decay functions to ultimately benefit cold chain logistics as well as supply chain and logistics as a whole. This chart shows a diagram of my research beginning broadly with supply chain and logistics and then getting into a subfield of that, which is food supply and cold chain logistics, and then ultimately getting into spatial optimization or route optimization and operations research with studies of the traveling salesman problem, vehicle routing problem, and knapsack problem. This picture shows clockwise a supply chain beginning with raw materials, then there's a supplier of raw materials, and then ultimately a manufacturer will make the product where it goes to a distribution center and is delivered to the consumer via an in-store retailer such as a mall or a Target equivalent, or it gets delivered directly to the consumer via something like Amazon. And as you can see, logistics is involved in every step of the process, and it's kind of what makes the supply chain go around. The traveling salesman problem states that if you have a starting point in X number of locations and back to the starting point, it asks, how do you calculate the shortest path? There's two ways to do this. You can calculate via an exact method, which uses brute force to manually calculate all the potential set of solutions, and you can use a heuristic, which will calculate a solution much quicker when you get into larger sample sizes, but it may not be the exactly correct answer, but it's typically near optimal. In the chart on the right, you can see with 10 locations, the formula is calculated n-1 times a factorial, which means 10 minus 1, which is 9 times 8 times 7 times 6. And for 10 locations, this comes out to about 362,000. And for 15 locations, it's approximately 87 billion. So you can see the computational complexity needed to take on a problem like this is immense as it goes well beyond 10 locations. The vehicle routing problem is simply multiple traveling salesmen. So it just means you have more than one vehicle and you have to calculate the number of routes for more than one vehicle. And you also have to calculate the number of vehicles that makes the problem most efficient. So there's added complexity with the vehicle routing problem. The knapsack problem. So the knapsack is thinking about a backpack equivalent to a semi-truck trailer or delivery van. So this basically means you have items with different weights and levels of profitability and costs that need to be packed into that semi-truck trailer or backpack or delivery van. And how do you do that most optimally? So this essentially is an inventory management question. And then with food items, you have temperature control requirements. So this adds another layer of complexity. This slide shows my dissertation chapter details. The main things I want you to pay attention to are what each chapter covers. So chapter 2 will go over the vehicle routing problem. Chapter 3 covers the vehicle routing problem and knapsack in conjunction. And the 4th chapter covers the traveling salesman. And on the right, you can see we begin with dense urban deliveries, then go to medium for the 3rd chapter. And then for the 4th chapter, we're going to focus on state by state or regional distribution routes. For chapter 2's research question, we ask, how can a dynamic vehicle routing algorithm be adapted to incorporate real-time constraints such as traffic, delivery windows, and temperature control, as well as weather for last mile logistics? For chapter 3, we ask, how can a hybrid optimization model increase between the knapsack and VRP, increase load utilization as well as route efficiency while minimizing spoilage for food supply chain and cold chain logistics? And then in chapter 4, we ask, how can the traveling salesman problem be extended to include perishability constraints, real-time disruptions and rerouting, as well as temperature decay functions to ultimately develop a new model? For the 2nd chapter and first problem statement, there's a few things that jump out to me with regards to problems in last mile logistics, and they are inefficient routing and lack of route optimization. So small to medium-sized food distributors do not have the necessary resources similar or compared to a company like Amazon to have proper route optimization. A lot of times these small to medium-sized enterprises are relegated to simply using a vanilla software that does not have the perishable constraints, or they're relegated to simply using spreadsheets. So route optimization and inefficient routing are pretty big problems within last mile logistics. Urbanization, people moving to cities, increased e-commerce demand, and increased fuel consumption, as well as increased carbon emissions, all exacerbate these challenges. And there's difficulty integrating real-time constraints as well as perishability constraints. The solution for this is to develop a dynamic vehicle routing model that includes delivery windows, traffic and weather and temperature control in this. And unlike traditional VRP models, we're going to introduce food-related constraints to this. And I will talk a little bit more about the 5 heuristics either in a later video. And I do not have time today to go over that in detail, but you can ask me about that after the video. For the 2nd problem statement in the 3rd chapter, we're going to look at the hybrid knapsack and VRP in conjunction. The food supply chain is highly vulnerable to spoilage, so we're going to take into account an inventory management bent in addition to the routing. So if you look at the fact that when you're delivering these items, some items have priority. So things like fish and ice cream may need to be delivered ahead of eggs and dry goods. So there's an added constraint there. And then also when you open and close the doors, so many times temperatures can rise. And oftentimes within the semi-truck trailer, there's different compartments with different temperature requirements. So all these things added together are related to the knapsack and will be an inventory management component that we'll focus on in addition to the routing. The vehicle routing problem and knapsack have not typically been discussed in conjunction. So what we're going to do is develop a hybrid model for both of these optimization problems. And we're going to try to minimize or increase routing efficiency, as well as minimizing spoilage and increasing load utilization. These problems are not typically studied in the context of cold chain logistics, so we're going to be able to make a novel contribution in this regard. For the 4th chapter or 3rd problem set, we're going to focus on the traveling salesman with regards to regional distribution routes. So the issues in food supply chain are not adequately expressed by the traveling salesman model, and route optimization for longer distribution routes has received little attention, and it's more focused on dense urban delivery. So give you an example of a constraint that we'll use is hours of service for the drivers. So typically drivers will have a set amount of hours they can work on a daily and weekly basis while they're making their delivery. So it's not like they can just drive 24 hours straight across several state lines to ultimately make a high priority delivery. They have to basically follow the guidelines set by the Department of Transportation. So we're going to dive into that a little more. And the solution for this is to develop a model within the traveling salesman that incorporates perishability, temperature decay functions, and real-time disruptions or rerouting. And we'll focus on basically incorporating the perishability as well as different states. So think Boise, Reno, Las Vegas, Phoenix, Denver, etc. And we're going to use kind of these longer distribution routes in our analysis. This is just a quick overview of my geographic study area. It's going to begin with Salt Lake City, which is considered the crossroads of the West. We've got I-80 running east-west, I-15 running north-south, and then also you have I-70 to the south running, connecting I-15. So I-80 hits Reno, I-15 runs through Vegas, hits Los Angeles, and I-70 hits Denver. This is my timeline, and thank you to my advisor and committee members. Dr. Richard Medina is my advisor. Dr. Simon Brewer is my co-advisor. Dr. Tom Kova is a committee member. Dr. Alex Hull is a committee member. And Dr. Reed Ewing is a committee member. Thank you very much for watching. I'm really excited to get into this research, and my goal is to eventually do something with it after from a business or software standpoint. Thank you.